Hello, good morning. My name is Jordan Pinto and welcome to my channel. Today we'll be talking about caching, paging, memory mapping techniques, everything about memory. So let's start with caching. So when we talk about caching, what does caching mean? So look at your table or probably in a library. You will notice that the most frequently used objects or the most frequently used books are placed in at the front of the shelf for you to access. uh, but and also on your table, the table you learn on, you most of the time put the books you recently used or the ones you would use again on the table. That is basically what caching does. So caching stores frequently used objects closer to you, that so that its retrieval will be quite faster. Think of it as your pocket where you keep your phone. You put your phone in your pocket so that you can easily retrieve it when you want to use it, since the phone is the most frequently used device on you. So how does this caching work? It works by standing at being like a middleman between the main memory and your processor. So it works as the middleman, takes information, the frequently used information and data instructions from the main memory, stores it in itself, and keeps it for easy retrieval from the when the processor needs to use the information or data or instruction. It easily retrieves it from cache memory and straight into the processor for its use. So talking about this, you just look at your table, you notice that your table has limited space. It can't literally store everything on your table, on your bookshelf. That's why it keeps the most frequently used books and items. That's the same thing that goes with caching. Caching has limited space, so it can't basically store a lot of stuff. It stores the ones you can use frequently. It doesn't store more than that. So next on our list is memory mapping techniques. Okay, so when we talk about memory mapping techniques here, we are basically talking about the way the processor or the CPU access the memory spaces available to them on the main memory. Yeah, and it determines how the CPU accesses memory spaces, whether for instructions and data or input and output operations. There are two major types of memory mapping techniques, which is the memory mapped I/O, which is the memory mapped inputs and outputs here, and we also have this an isolated inputs and outputs. So when we talk about the memory mapped I/O, it's this technique in this technique, I/O devices are treated as if they are memory locations here. The same address buses are used to access both RAM and I/O devices, which I/O stands for input and output devices. So how does this work? Each input and output device is assigned a unique memory address, and when the CPU reads or writes to that memory address, it actually interacts with that device instead of the RAM. So you that is basically how it works. The advantages of the the memory mapped inputs and outputs is that one is simpler, its design is very simple, and the same instruction sets for memory and it uses the same instruction sets for both the memory and the inputs and outputs. Secondly, it's effective and efficient for systems with fewer input and output devices. So if your your device you're using uses fewer inputs and outputs, the memory mapped input and output mapping technique is very good for it. The disadvantages here in it is that it reduces the amounts of addressable memory because input and output share the address space with the RAM. That's the only downside of it. The second memory and the memory mapping technique, the second category of the memory mapping technique we'll talk about is the isolated inputs and output. So isolated devices have separate address spaces for memory. The CPU uses space instructions in and out to communicate with devices. So how does this work? The input and output devices are not part of the memory address spaces. The CPU uses dedicated set of instructions to access input and outputs. The advantages of this is that full memory address spaces remains available for RAM, and clear separation between the memory and the inputs and outputs. So that's it. And the disadvantages for that is that it requires separation. It requires separate instructions for input and output operations. So in the memory mapped input and output, the same fewer instructions are used, but this one more instructions are used because different instructions are used for both the input and output and the memory, and slightly more complex in CPU design. So another memory mapping technique is called the virtual memory mapping technique. It maps virtual addresses used by applications to physical addresses in the RAM, and is managed by the memory management unit and page tablets. Another memory mapping technique too is the cache memory technique. This helps determine how blocks of main memory are placed in the cache. So that's how the cache memory mapping techniques work. So let me go deep into the cache memory mapping technique. It first checks the cache. When the CPU needs data, it first checks the cache. If the data is found in the cache hit, if the data is found in the cache is called that process is called a hit, and if it's not found, it's called a cache miss, and it fetches data from main memory and loads it into the cache. But where exactly in the cache should the memory block go? This is what the cache memory mapping technique does. It's one, the types of memory mapping techniques is the direct mapping. Each block of main memory maps to exactly one cache line, and this is how it works. The cache location is equal to the block address, and the memory is equal to the block address. One possible location for each block. So there's only one possible location for each of the blocks. And we also have the full associative mapping technique. Any block from the main memory can go into any line in the cache memory. So how does this work? The cache is searched entirely to find the block using the tag, and no fixed position for the blocks. There are no fixed position for each block. So we also have the set associative mapping technique. A compromise between the direct and fully associative mapping techniques. So how does this one work? The cache is divided into sets. Each set has multiple lines. Example, two-way, four-way lines. A block maps to one set using a block address. Within the set, the block can go into any line. So that's basically memory mapping techniques, and we'll be talking about paging next. So what is paging? So paging is breaking the physical memory and logical virtual memory. So paging is a memory management technique used in modern operating systems to allow a process memory to be non-contiguous, making it easier to manage and utilize memory efficiently. So paging breaks physical memory and logical virtual memory into fixed blocks. So when we say pages basically are the fixed size blocks of a logical virtual memory, and frames in a page, or let me say frames, is a fixed block of physical memory. So the operating system keeps track of all this using page tables that maps each virtual page to a physical frame. So how does this work? When a program runs, it thinks it has a larger chunk of contiguous memory. The operating system breaks this logical memory into pages, and the physical memory RAM is divided into frames of the same size. So a page tablet maps each page to the frame in the RAM, and the memory management unit uses this page table to translate virtual addresses into physical address. So that is basically what paging means. So in conclusion, I forgot to talk about the memory hierarchy, or the memory hierarchy, whatever it's called. So this is the memory hierarchy design or something. It basically shows how memory ranks in levels. So at the top level, we talk about is the CPU registers. This is basically made up of flip-flops, and is quite so far the most fastest memory associated with computers. So this one has the least space, or the smallest size in the memory hierarchy, and is the fastest amongst them. Then now we go to the cache memory. So now cache memory is the next, which is quite faster than the main memory, which is the main memory, the memory sticks you see in your PCs most of the time, which is the DRAM, the dynamic memory. We move next to the magnetic disk, which is the disk storage. This is basically what's the name your hard disk drive. Normally the the SSD must come before the hard disk, but this time there's no SSD here, so now the memory magnetic disk, which is the hard disk, is in now. Then next we go to the optical disk. The optical disk basically is sometimes the what's the name of this disk? The CDs. The CDs have the there are types of optical disc. Then we have the magnetic tape. The magnetic tape, but in our old days, you remember there used to be this tape that they insert into the old PC computers, what's the name, the old cameras, that keeps track of data. So that is the magnetic tape, and that is the least. So as it goes down, it increases in capacity. So the magnetic tape has the highest disk space, or the highest space, followed by optical disc, magnetic disc, memory, main memory, then cache memory to CPU registers. Then in price and time access is also the same way, from CPU registers to memory magnetic tape. So in conclusion, we talked about caching, which basically tells you how the computer interacts with the memory with the middleman called Mr. Cache. What it does is that it stores frequently used information, keeps it into its space, and is easily accessed by the processor to do basic tasks. And now we also spoke about the memory techniques, where we spoke about the two categories. You have the memory mapped inputs and outputs, and there was a name. We also spoke about the isolated inputs and outputs. Then we also spoke about types of memory mapping techniques, where we spoke about the cache memory mapping techniques and various memory mapping techniques. Then we also spoke about the memory hierarchy. That is what we are seeing right now. And we spoke about what paging is, where the computer, a program thinks it's using a big and continuous space, a disk memory space, but it's just using a fraction of the main physical memory. So that's all I have for you today. Catch you on the next one. Thank you.